So good afternoon, everybody. I hope you can hear me. This is Ernesto Damiani. I'm really pleased tonight to have the opportunity to introduce this evening keynote. Well, evening or afternoon, wherever you are. So this the speaker tonight is Professor Selcuk Candan. He is a friend, but he is really a top researcher in the area of management of imprecise information, of imprecise data, of uncertain data. He's the director of the ACU Center at Arizona State University, Cascade Center. And he's such a long CV that's very difficult for me to summarize it in a few lines. He has led many of the leading events for our community. He has been the general chair in SIGMOD. He's an ACM distinguished scientist. He contributed to the fields in so many ways that it's hard for me to summarize them. So I'm really glad that this evening and interested in being part of the audience for this keynote that Selcuk will deliver to us. So without further ado, I would like to leave the stand to our friend, colleague, Professor Selcuk Candan. Thank you for accepting our invitation and being our keynote this evening. The stand is yours.
Thanks a lot, Ernesto, for the very, very kind introduction. I am very honored to be here with you and with the rest of the audience. And I'm hoping that basically we can start the PowerPoint presentations so that I can start. Perfect. Great to see that everything is working perfectly. So again, Ernesto, thank you for your very kind introduction. I'm a professor of computer science engineering at Arizona State University, and I'm also director of Center for Issued and Scalable Data Engineering, Cascade. And today I'm going to try to tell you guys a little bit about basically my team's research on smart data services for what I will call sense-making in human-centered dynamic systems. Of course, there are a couple of, words here: smart data services, sense-making, human-centered dynamic systems. I will try to explain basically what I mean by those, and I will try to give some context to the type of work that basically my team and as well as basically researchers out there are sort of trying to tackle. And as basically sort of as time allows, I will also try to basically give maybe some specific research outcomes based on some of the basically work that's happening through the funded grants that we have. But before doing that, let me just do this 1 second. Okay, before basically starting, I would like to thank the IEEE Services Congress for giving me the opportunity to be here to give this keynote as part of this conference. Of course, General Chairs Elizabethina and Hong Mei, steering committee, the entire steering committee in the person of the committee chair Carl Chang, the symposium general chair Rang Chang, and the program chairs in chief Ernesto Damiani and Zi Jin. I would like to basically personally thank to them for giving me the opportunity. And also, before starting my presentation, I would like to also take this opportunity to remember my dear colleague, Michael Gold from Arizona State University, who we lost earlier this year. He used to be a member of the IEEE Technical Committee for Service Computing. He was also the chair-elect for the technical committee. In 2019, he was elected as the chair-elect. And also, he was a recipient of the 2016 Outstanding Leadership Award from the technical committee, especially for his work on service computing, obviously. And his work basically included a significant amount of work on data, big data, especially basically in dynamic systems like supply chains. So he was basically a very close colleague, and I would like to basically take this opportunity before starting basically my research discussion or the keynote. I would like to basically remember him. Given this, basically, let's go ahead and start smart data services for sense-making in human-centered dynamic systems. What do I mean? Right? So it is obvious, right? So it should be obvious for all of us, right? So in computing, right? So is that we live in communities, right, so that are dynamic systems, right, so interspersed with highly complex natural and man-made processes, right. So, and many of the services, basically applications, tools, and services that we develop are essentially to support these complex dynamic systems. These basically start from things like smart offices, supply chain management, as I mentioned, education, smart rooms, but basically extends to things like public health, rehabilitation, and other things that are healthcare related. So we live in complex and dynamic environments. And key enabler here, of course, basically from my background, at least from my perspective, and that's basically why I'm giving this keynote, right, is the data, right? So data is basically, for many of the applications that I mentioned, let it be smart people, let it be smart living, let it be smart mobility, let it be smart economy, let it be smart environment, let it be smart governance. For many of the basic applications that we can basically classify under any of these smart services, right? So data is the key enabler. Okay, so for example, if you basically take something like a dense urban environments, or basically a smart city kind of setting, right, to be able to provide any of the services that basically we are mentioning, we need to have meaningful situational understanding, and we cannot have basically situational understanding, right, so in such human-centered environments, right, without having access to data. An example is basically smart cities and IoT, right? So obviously, basically running a smart city, right, so requires a city system, right, so that is able to gather and integrate data, right? We also need, on top of that, a real-time and continuous analytical framework, right, so to make sense out of the data that is basically being gathered, right? And we also need basically a layer on top of this, right, so that's going to support data-driven urban modeling and simulation and forecasting. Right, so smart cities and basically what we generally call as IoT, right, essentially a data-centric platform. This also basically shows itself if we quickly sort of dive deep a little bit on basically the IoT platforms and their services. If we look at that, we'll basically see that the data services, right, so are pretty prominent there, right? So multimodal, multi-platform, distributed and scalable real-time analytics, data fusion, machine learning, and provenance, right? So these are basically core IoT services that basically we need to provide for a smart city. And obviously, basically, these are all data-related challenges, right? So the summary is that only when complemented with real-time integration, analytics, and pattern discovery, right, and human-centered technologies, right, so to support data-driven decision-making based on this continuously digested and updated data, right, only then we can actually start calling IoT technology or any the technology that is supposed to support real-time human-centered environments smart. Right, so essentially smartness basically is conditioned, very heavily conditioned on our capability to handle data or deal with data. Now, of course, there are many challenges, right? And basically, a large portion of this talk is going to be about challenges, and I might basically, depending on the time, right, so I might actually show some solutions, right? So the whole point is really the challenge, right? And one of the first challenges and that we need to recognize is basically these human-centered systems, right, so are inherently multi-scale, right? At the small end, right, so we have basically personal environments, or if we just look at a bit larger than that, we have buildings and building clusters in which humans live, right? Human lives and work, right? These are what I would call small in the sense that basically they are usually under a single administration. Their spatial scale is small, at most basically a city block, right? If you are talking about the building cluster, right? And their temporal scale of the decisions, observational decisions that we need to make is basically minutes to days, often, right? Okay, of course there are exceptions. I mean, everybody can come up with exceptions. I'm just basically making very high-level generalizations, right? At the medium scale, right, so we have basically city scale things, right? So we have basically, for example, a good example for that is emergency response, right? This tends to be city scale, right? Of course, we can have small emergencies and large emergencies, but this tends to basically be city scale. And emergencies usually basically develop days to weeks, right? For example, a hurricane could basically be an emergency. It develops basically in a week time frame. It hits a city, usually large, and basically it involves its administration scope is largely cooperating agents and administrative units, because a city generally tends to basically be under a single administrative unit. So you have basically cooperating agents that basically are interacting and making decisions in such a setting. And on the other side, right, so we have large-scale dynamic systems, right? So a good example for that is planning for epidemics and pandemics, right? So these basically develop over weeks to months, right? And they basically hit an entire nation often, or many times maybe an entire continent, or basically in the COVID era that we are living in, entire world, right? And they also basically often involve competing interests, right? So because you might have basically multiple agencies that are under different administrations, you can have nations that are competing for resources, right? And so that basically give some other type of basically challenges in terms of data-driven decision making, right? And a key challenge, right? So that basically sort of cross-cut all of these is that in many cases, right? So although the way I presented basically it sounds like basically these are sort of separate scales, in many cases, right? So these different scales, right? So can coexist, right? And basically the processes at different scales, right? So can interact with each other, right? And this basically makes human-centered dynamic systems especially complex and especially difficult basically to handle effectively and respond effectively. Okay, so the summary of basically the previous slide essentially is that because of the size and complexity of the data that we often have to deal with, right? And the very special temporal scales at which basically the key process operates, right? Experts that needs to make basically sense about the real world, either for situational awareness, right? What is happening right now, or basically to predict the future situations so that they can develop interventions, right? They often lack the means to understand and predict the relevant processes, right? So that's basically a core challenge that basically we need to, if we are going to basically, if we are going to use this data, we need to resolve. So again, going back to basically our key enabler, right? So data is a key enabler, that's true, right? But then the question becomes, right, so can we actually leverage, right, so big data for tools and services, right, so to enable communities where us, inhabitants, live and work collectively in harmony, right? And where the community functions, right, so the entire community functions is a system that is resilient, self-sustaining, and livable. Right? So saying that data is a key enabler is not really sufficient, right? We need to basically, we need to develop tools and services, right? So that basically actually make our communities resilient, self-sustaining, and livable, right? And this especially becomes important when we think of basically urgent challenges like sustainability, right? So urgent challenges like emergency management and urgent challenges like COVID-19, which essentially is practically every aspect of our lives, right? So the summary of the summary, right, is that can we make sense and support decision making with data, right? So that's basically what essentially everything, all of this essentially boils down to, right? So what does sense making? Remember, I use this term as the title of my presentation. But I didn't define what sense making means, right? So, and of course, we can have different definitions of this, right? So, when I hear some word, right, and again, I'm not a native English speaker. When I want to understand what it means, I go and look at the dictionary, right? So if you take a look at this term sense in dictionary, right, so we'll see that basically the first meaning of this first sense of sense, right, is actually coming from Latin sentire, and it actually means perceive, right? So these are basically essentially any faculties, right? So sight, hearing, smell, taste, right? That basically is involved in perception, right? The second meaning of sense, or second sense of sense, is about awareness and understanding, right? So awareness basically means the ability to make inferences, right? So about what is happening, right? So and understanding means, okay, to actually be able to map the perception, low-level perceptions, right, so to high-level concepts and categories, right? So if we are talking about essentially sense making in the real world, right, this essentially involves what I call smart data services, right, that maps low-level data, right, so, and maybe streaming data and knowledge bases, right, so which are often only feelings and measurements, right? So that basically collect as raw data, right? And then map those, right? So to a high-level awareness, understanding, and control, right? So anything essentially that we can use, right? So to bridge that gap, right? Essentially, is part of a smart data service, right? So that's essentially what I mean by sense making. Now, so what are the smart data challenges in such a dynamic world, right? So, well, okay, we all know about the 3 V's, right? So volume, velocity, variety, right? So these are sort of the 3 V's of big data. Actually, there are more V's, like veracity and others, right? But for now, let's basically just focus on the 3 V's, right? So volume, velocity, variety, right? So these are commonly known as basically data challenges, right? So data is large, data comes fast, and data basically is heterogeneous and in many different formats. Right? Now, in my lab, we actually say that actually these 3 V's might be actually not too difficult, right? So they are difficult, but there are actually other challenges, right? So that we need to be dealing with, right? So around these 3 V's, interacting with 3 V's, but distinct from these 3 V's. Right? So the first of these is what I call HMLE challenges, right? So the data is that basically we need to deal with is often high dimensional, right? So this is happening because we are basically observing in a complex system. We are observing different aspects of a complex system, right? And we have basically many different observation points, right? And this basically means that our data is inherently high dimensional, right? In fact, I mean, even if you have a single observation, even if you are just getting a video stream, right? So that itself is high dimensional, right? So, but even if we forget about that, if we say that each of the observations are single dimensional, right? If you are observing a smart environment, like a smart building or smart city, your data is inherently high dimensional, right? So your data on top of that is also multimodal, right? So because you are observing the real world in all its modalities. This is kind of related to variety, but it's different. Right? So variety really talks about different formats. Multimodality means, right? So you need to deal with time, and you need to deal with space. Maybe you also need to deal with hierarchies, and maybe you need to also deal with graphs, right? Because different data, right? So have inherently different modalities that require completely different representations. And that also means that they all need different type of ways of dealing, different ways of processing, different ways of analyzing, different ways of visualizing, right? So the data is inherently multimodal, right? Data is highly interlinked, right? So because we are observing an environment, so everything is kind of related to each other, right? So there are linkages, right? So some of those linkages we already know, right? So because they are part of basically the topology that we are aware, right? And part of those linkages, right? So we don't know, right? So because those are the linkages that we need to maybe discover, right? So to provide our smart services, right? So data is heavily interlinked in such scenarios, right? And also evolving, right? So data is evolving. Now this is similar to velocity, but it is different, right? So you can have a very fast data, right? So but it may not evolve, right? So the underlying structures may not change, right? But in a real world, in a dynamic world, in a real world, right? So the data evolves, right? So things change in the real world, right? So there are fundamental structural changes that are happening, right? Which essentially means that basically the models that you learn in one day, okay? So the thesis that you have in one day about the operations of the world, right? So it's not going to be the same as the following day, right? This means that, right? So you need, okay, right? So to be able to deal with basically the changing models, changing understanding. Right, so this is related but different than velocity. You are not only dealing with the speed of the data, but you are also dealing with the fact that you cannot basically sit idle. Right, so you always need to look at the world, and you always need to basically come up with new understanding of the real world. world, right? So those are basically what I call the HMLE challenges, right? On the other side, right, so we have basically SINT challenges, right? So sparsity, right? So what does sparsity mean? Well, data might be a lot, right? So maybe you are getting a huge amount of, maybe you get 2 terabytes of data, right? So per day, okay, you get a lot of data, right? But is that data enough to support decision making, right? So, and many times it turns out that even if you have a lot of data, right, so the data is not sufficient for you to make sufficient inferences, right? So this is a challenge, right? So yes, I have a lot of data, right? So but for the decision that I need to make, do I have sufficient data, right? So many times we don't have actually sufficient many data. In fact, many times you need to make especially, for example, if you are responding to zero-day attack, right? So in an environment, right? You actually don't have any data, right? So it's the first time you see an event, right? So those are basically real challenges that you face, okay, when you are operating in the real data. In fact, in that case, volume is your friend, right? So if you have more data, the better, right? And sparsity often basically combines with imprecision and noise, right? So in the real world, observations are often imprecise for various reasons that we can get into, right? But they are also noisy. Okay, right, and these basically actually complicate real-world understanding and the precisions, because especially when they complement with sparsity, right? So they make the job of sense making very, very, very difficult, right? So even if you have a lot of data, if it is noisy, right? So you need to basically come up with ways to deal with noise handling. Right? So those are some challenges, right? And obviously variable trust, right? So because if you are talking about the open environment, right? Are you trusting all of the streams of information that is coming to you, right? Maybe you do trust all of your data if you are operating on a building, right? Because it's under the single administration, right? But you might not trust all the data that you are receiving in a basically setup where you have multiple agencies that are basically maybe even competing interests, right? So you might not be able to trust all your data. Even if you are actually operating on a single entity, right? So you might not be able to trust data, okay, because of faults, right? So faults are real, okay? Building systems have faults, planes have faults, right? So you need to be able to deal, okay, right? So with the issue of variable trust, right? So do you trust everything? How do you basically ensure that the decisions are trusted, right? So how do you design? How do you make sure that the scalability that you are basically trying to achieve is complemented with assurance, right? So those are real challenges that needs to be resolved. Now, of course, again, the talk is about basically human-centered dynamic systems, right? These bring, right, so not pure data challenges, right, so but data-related human challenges, right? So the data source, right, so often is in such systems is human, and also the final consumer in many cases are human. Not all the time, yeah, not always data source is human, not always basically the final consumer is human, right? So, but in many cases, right, so both data sources or right, so the final consumer is human, right? So this basically brings, okay, right, so what we will call the human challenges, right? So first of all, privacy, right? So we need to basically be dealing with privacy. We cannot basically assume that just because all of the data is available, okay, right, so it is usable. Right, so data might be collectible, okay, but it might not basically be available to the decision makers, at least in its own raw form, right? So we need to basically deal with the privacy, okay, right? And again, this is one of the challenges that we face in the COVID era, right? So there are many decisions that basically people like to make, right? So maybe even basically based on their own behavior. I want to know basically how to behave. Do I need to know basically who around me have COVID disease? But I might not be able to do that because of privacy concerns, right? So all decisions that we may want to make may not be enabled because of privacy concerns, right? This combines, right? So with basically the limitations of the consumer. So this was the privacy is usually the data sources. Challenge, right? So, but we also have data consumers challenge, right? So accessibility, right? So this is a big challenge, right? So because if I have a large amount of multi-modal, multi-dimensional data, right? So how do I basically make this accessible, okay, to the decision maker, right? So how can the decision maker explore or make use of this large amount of data, right? How can I explain? I mean, okay, I can make the data accessible, maybe, right? Okay, but remember, from these data, I'm making basically decisions. I'm making forecasts, right? So I need to explain to the decision maker, okay, which is often a human, right, why I'm making those recommendations, right? So based on which data, based on which assumptions, based on which processing, okay, right? So I'm able to basically make those recommendations, right? So which means that basically I need to explain, right? So that also goes with assurance, right? So I need to assure the decision maker, right, that the recommendation that I'm making, okay, are actually, okay, things that that decision maker can rely on, right? So these are basically the human side of the challenges, right? So privacy, explainability, and accessibility, right? So actually, it turns out that the three V's that we have, right? So they are often actually the many times basically easiest things to deal with, right? So if you are trying to provide smart data services, you actually have more acronyms to actually consider, right? So we, as basically sort of we bootstrapped the Cascade Center. Okay, and this was a couple of years back. Please take this with a few grain of salt, because this is not exactly yesterday. So this is a number of years back, right? But not too far, right? So let's say basically 3 to 5 years back, right? So we basically, we brought together, right, so a large number of entities, right, so private, public entities, right, so in a room, right, so we basically essentially asked what frustrates you today, right, so that basically we have the center, right, so and we want to basically solve your problems, right, we want to develop services, right, so that's going to actually address your real concerns, right, so what frustrates you today? So what I want to do is I want to share some of the outcomes of this, right? So again, so these are not necessarily my outcomes. So these are actual outcomes basically from these meetings that basically we had, right? So we asked basically these entities, right? So what are the 6 most critical sort of gaps that you see in your organization or in your technical capabilities, right? So this is basically where you guys are. This is where you guys want to go. What are the gaps? Yeah. So it's always instructive, right? So this is basically because these are entities, right? So that are actually trying to solve real world problem out there, and many of these real world problems are human centered, right? So so the gaps that basically these folks identified, right? So which basically I think was valuable to us, because we use this information for our center as well as for our hiring of faculty, as well as we use it basically for our curriculum developments, right? So, but it can also be useful for you guys, right? So the first gap that basically was identified was temporal and spatial analysis, right? So this came as the first ranked, okay, out of the interactions that happening. So this came as basically top rank, okay, right? The second gap was about summarization, cleaning, visualization, and anomaly detection. Right? So as you can see, so these are actually going to access, right? So the human decision maker, right? So want to be able to, right? So access, right? So a complex data, right? So that's available, okay, in an interpretable manner, right? So it wants the data to be summarized, clean, and visualized. And also, since the hunting for anomalies, right? So for a human entity is difficult, right? So we see patterns, anomalies not as well, right? So not always, at least, right? So also anomaly detection to basically essentially point to that needle in the haystack, right? So that was the second gap that was highlighted. So the third gap, okay, that basically these folks highlighted were real-time processing of data. Right, so they basically highlighted media analytics as being an example, right? So real-time processing, okay, of streaming data as a challenge, and this makes sense, right? So because, as I said, so these entities, right, so operate in the real world, right? So they are in human-centered environments, right? And that basically means that they need to provide services in real time to their consumers, which means the real-time processing becomes critical, right? So this was the third thing. So this is ranked order, right? So in third thing that basically was highlighted. Okay, the fourth, okay, was making unstructured data queryable, right? So again, you make observations in the real world, right? And you are basically essentially many times observing unstructured data, right? So because you have sensors, your sensors are sensing, Okay, maybe there's some structure, but that structure is not available to you early on, right? So because you just put your sensors to a particular location, right? So you don't know the underlying data, right? And maybe you get a lot of data, so you need to prioritize this data, right? So, and maybe you need to actually remove redundancies on this data, or basically identify gaps in the data, right? So that basically data becomes useful. Right, so these were basically highlighted as basically key knowledge gaps or key services, right? So that basically would be are lacking, right? So in current platforms or current systems, right? The fifth gap, okay, that were highlighted by these individuals, right? So or these entities, right? So was graph-based models. Right. So again, this goes to the fact that basically many things in the real world are interlinked. Right. So you need to be able to discover those linkages. Okay. Right. But as soon as you link things, right, so things become more complex. Okay. Dealing with graphs is more difficult than dealing with trees, hierarchies. Okay. Dealing with hierarchies are more difficult than dealing with sequences. Okay. And dealing with sequences is more difficult than dealing with sets and vectors. Right. So if you just basically sort of think about basically the sort of the data sort of representations, right? Graphs are difficult, okay? They are difficult both in terms of processing, storing, indexing, but they're also difficult in terms of actually making sense of, right? So graph-based models, okay, right? So was highlighted basically as a key knowledge gap, right? So by these folks, okay, right? And the sixth gap, right? So which emerged, right, was the performance and scalability, right? So and distributed architectures. Okay, right. So essentially, these folks said that we need performance and scalability as well, right? But this actually emerged. It's very interesting, right? So we were not necessarily expecting this, right? So this actually emerged only after, right, the other challenges. So basically, the V, right? So the V, one of the V's, right? So the volume actually emerged as the third one, right? Okay, but the velocity, right? But the first V that people usually refer to, which is volume, right, actually emerged as the sixth one, right? So people said, actually, you know what, the other things, right, so are more important for us, right? So because our consumers are human beings, right? So we are really operating in dynamic environments, right? And we need actually some other tools and some other services, right? So before actually think of scalability. Right? Now, so if you basically sort of gather all of this, right? So into basically sort of 5 service groups, right? So integrated, federated, scalable data storage, analysis, and modeling, right? So integration, federation is important, right? So this basically, again, these were the service groups that basically were sort of identified. In this case, not ranked order, right? So the service groups that were identified by this group, right? So integrated, federated, scalable data storage, okay, analysis and modeling, right? So this was service number 1, right? Service number 2, right, so is making unstructured data queryable, okay? This was identified as service number 2, okay? Service number 3, network analytics and entity analytics, okay, right? Service number 4, model discovery, causal discovery, okay, right? And new emerging patterns. Right, so in a sense, basically, sort of this is part of making sense, right? So you basically take the raw data and you are basically mapping basically essentially service number 1 and service number 2, right? So preparation, right? And service number 4, okay, is about actually making sense, right? And the service number 5 is actually about validation. Right, so because you can have the models, but are they true? Right, so you need to basically validate, and this goes back basically with the change. Even if your model is valid today, your valid basically may not be valid tomorrow. Right, so you need to have the ability, right, so to validate models, okay, so that you can support forecasting. Right, so you need to make sure that as the time moves, okay, your models stay the same. Right? So another way basically to visualize essentially these 5 sort of services, right? So is basically by this sort of diagram, right? So this basically shows that essentially sensemaking is not a single shot thing, right? So you need to basically continuously, okay, right? So provide a set of services, right? So that feed into each other, right? So the first one is sensing and integrating, right? So you need to basically be able to collect using, for example, IoT devices or other basic data sources, right? So input data, okay? You need to unify, integrate these, okay, right? In a way, okay, that is basically then consumable, right? So by other services that you want to provide, right? This in the second step, right? So comes analysis, simulation, and prediction, right? So now that you have this unified data, right? So you need to basically support data-driven model learning and analysis, okay, right? And this can actually also involve, right? So once you have the models, right, so data-driven models, so you might also have basically other physical-based models at this stage, right? You also need to basically be able to use these, combine these together, right? Okay, so that you will support basically either basically forecasting, either algorithmic forecasting, okay, or basically maybe simulations, right? So now that you have models, you can actually simulate the real world to support predictions and forecasts, right? Okay. But this is not enough, right? So as we have seen before, right? So you need to be able to validate and interpret, right? So you need to basically use, right? So the observations that you have, right? So to be able to go back and validate the models that you have learned, right? Okay, and you need to be able to interpret, right? So these these model outcomes or basic validation results, right? To convince, right? So the decision makers, right? So that basically the precision, the predictions or forecasts that you are making are trustworthy and accurate enough, right? So that's basically sort of the fourth, so third thing that you need to do, right? And the final step, of course, right? So is about act and adapt, right? So act means you need to act in the real world, right? So you need to basically you make these changes. You need to implement interventions. Right, so you are any intervention is changing the world, right? So you are basically making decisions to maybe close schools, right? So you are making decisions to move resources from one part of your city environment to another one, okay, right? So because the models basically tells you that that's the good thing to do, right? Okay, but you also need to adapt, right? So that goes back to basically the evolution, right? So you not only need to act in the outside world, right? But you also have to, right? So but you also have to, right? So go back, okay, to your own services, right? Okay, and you need to adapt them, okay, because the real world changes, right? So which means that, okay, right? So your service delivery also need to change, right? Your data collection may change, okay, right? Your models need to change, right? Right? The amount of resources that you allocate to various tasks may need to change, okay, right? So maybe you are allocating some amount of resource to noise removal, okay, and maybe data becomes more noisy, and now you need to basically put more resources, right? Or maybe basically the change increased, okay, right? So now you need to basically put more cycles to change detection, okay, right? So the way basically your services are implemented, okay, right? So not only your models, but the way basically you discover those models, right? So using basically your service infrastructure, right? So you need to adapt, okay, right? So those basically are essentially, okay, what we call this sense, integrate, analyze, simulate, predict, validate, interpret, and act and adapt cycle, okay? And not that this is a cycle, right? So this never stops, right? In fact, it is, I mean, it's calling it a cycle is also a bit misleading in that actually in your service infrastructure, you are probably doing all four of them simultaneously, right? But at different stages, right? So while you are sensing, integrating, okay, right? So something, okay, you are analyzing and simulating something else, okay, right? While you are analyzing and simulating something, you are probably validating, interpreting the analysis results from the first, from the previous executions, right? And while you are validating, interpreting these results, you are actually acting and adapting based on the previous, one cycle earlier, right? So these actually occur in your service infrastructure, most likely constantly. Okay. Now, so given that I set up, right, so this sort of act, sense, integrate, analyze, simulate, predict, validate, interpret, and act and adapt sort of cycle, right? I hope I motivated it sufficiently well, right? In the next, I guess, remaining 20 minutes or so, right? So I want to basically touch to two sets of research that basically is happening in my lab, right? So the first set is what I will call simulation as a service, okay, right? The second set will be the time series analytics, okay, multivariate time series analytics as a service, right? So those are basically sort of the two sets of basically research that basically is happening, okay, right? But again, I don't know how much time I will have, right? So I will basically start with one, okay, right? And I will try to basically give some overview of that, right? And as the time allows, right? So I will basically also touch the other set of research questions, right? So which involves causal learning and other things, okay, right? But let's start basically with this simulation as a service, okay, which is basically sort of the label that we are giving to this set of projects. Essentially, it's DataStorm, and this is basically about analysis, simulation, prediction, and validation interpretation, right? So essentially, the research that basically we are sort of, and I'm highlighting here basically several research projects, right? So basically the different research projects are essentially tackling sort of different sub-problems and involve different applications, right? So you will see that if you look at that, there are some research projects that involve epidemics, there are some projects that involve basically disaster scenarios, right? And there are some other projects that involves basically what we call 4C modeling, conflict, cooperation, and complexity. Right? So there are basically these different aspects of the work, but let me basically start with the motivation. Right? Now, obviously, disasters are bad things. Right? So according to 2010 World Disaster Report, just in 9 years, right? So disaster resulted in 1 million casualties, affected an additional 2.5 million, and caused a loss of 1 trillion. Right, so basically disasters are bad, right? And obviously epidemics are also bad, right? And I guess this is the easiest sales pitch that I can have, right? Because we are living through this, right? So all of our basically supposedly smart services, right? So are now being directly affected, right? So from the pandemic that we are living through, right? So our communities are affected, our living definitely got affected, right? Our economy is being affected, right? So our mobility is affected, right? So the way basically we move within cities or across continents, right? So is affected basically from an epidemic, right? So which means that our services are basically being affected, right? Again, disaster preparedness and response is important, right? So we need to basically be able to forecast disaster processes. This could be epidemics, right? So we need to basically forecast where is this disaster, okay, is going to hit precisely, okay, right? As precise as possible, right? We need to be able to assess the impact of the interventions, such as basically evacuation or travel controls, right? Okay, and we also need to estimate the likelihood of secondary disasters, right? So it turns out that disasters don't come alone, right? So one disaster sort of begets another disaster, right? So if you have a hurricane basically has a sort of as a consequence, right? So may have basically airborne vector diseases, right? So it can basically cause a hurricane may basically cause mosquitoes, right? So because there's a lot of water, right? And those mosquitoes can cause actually an epidemic start, right? So in fact, another way hurricanes has an impact on epidemics is that because it brings lots of people together, right? So it basically moves people to basically centers, right? So and poor living conditions can actually cause epidemics, right? So there is basically not only primary disaster but also secondary disasters, right? And obviously there is not much room for error, right? So because both action and inaction, right, so have high costs, right? So these are basically in economic, you can basically put money into that, but also basically human lives got affected, right? So you cannot basically not act, right? So you need to act, but the question is that what is the right action, right? So in fact, inaction is an action, right? So, and then you don't have much room for error, right? The challenge, obviously, right, is that as I'm hopefully motivated so far, right? So these are complex and dynamic processes, right? So disasters involve hundreds of interdependent parameters, right? They involve multiple layers and geospatial frames. Okay, things might be happening at a city level, things might be happening at a nation level, things might be happening at the international level, right? And basically, these are dynamic processes, right? So which means that things change, right? So what was yesterday is not today, right? So what is today is not tomorrow, right? So these are dynamically evolve over time, right? So which means that not only you need to deal with this complexity, right? So in terms of number of parameters and in terms of multiple layers of processes, right? So you also need to have continuous adaptation and remodeling, right? So the second challenge, right, so within this context, right, so is cost and sparsity, right? So given the unpredictability of the disaster, and given that basically you have various interdependent agencies that might make basically completely independent decisions, right, so that are not in the control of basically one decision maker, right? So if you need to make a decision, right, so through, say, simulations, let's say you have a good model, okay, let's assume that you have a model, right? So lack of model is some problem, right? So let's assume even if you have a good model, right, you need to basically be able to generate, okay, thousands of simulations, right? So you need to be able to basically generate thousands of simulations, right? So each basically sort of representing, right, so a different but plausible scenario, right? Now, the running of these simulations is obviously costly. Okay, right? So, and depending on the setting, I mean, if it's a pandemic, right, so maybe you'll allocate 1 week to run everything, right? So, but if it is basically a hurricane that's approaching, right, so the running all the related simulations, right, so it's costly, right? So that needs to be taken into account, right? Okay, and given the very large parameter, very much parameter space, okay, and given the cost of actually executing these simulations, right, so many times, okay, what we call simulation ensembles, right? So which are essentially the set of simulations that you run, okay, right? So based on this scenarios, each basic simulation being a scenario, right, is inherently sparse, right? So you can run thousands of simulations. 1,000 is nothing, right? So if you have 100 parameters, right? So each one is taking 2 values, right? So it's again 1,000. What's 1,000 simulation? What is 10,000? What's a million simulation, right? So basically, simulation ensembles, right, so become inherently sparse, right? As I mentioned, right, so simulations also need to be coupled, right? So they are continuous, right? So because, as I said, so I need to basically, as real world data arrives, right, so I need to revise my simulations, right? So because I know more things about the world, right? So world, basically, either I have more data, right, so about the static world, or the world changed and I have new information about the new world, right? Which means that basically I need to be able to revise my simulations, right? So and model my models, right? So I need to be able to decide what additional simulations I need to run, right? But also many times these simulations are coupled, right? So for example, a hurricane simulation, okay, right, so may need to inform my disease simulation, right? Or a wind simulation might need to inform, or flood simulation might need to inform my human mobility simulation, right? And in many cases, right, so these simulators are independently developed, right? So there is you can get a hurricane simulator, right? So you can have a surge simulator, okay? You can have a flood simulator, and you have a human mobility simulator, right? So these are independent simulations, right? So the question essentially becomes, okay, right? So can you actually couple these, right? So these independently hooked basically models and simulations, right? So and have an end-to-end view, right? So of your evolving disaster, right? So and how do you do that? So this basically brings what we call DataStorm services, right? So this is basically model and simulation ensemble management as a service, right? And this basically involves, right, so given a parameter space and a budget, right, so selecting the simulations that you need to execute, right, so to support effective decision making. Right? So you don't want to blindly, given the cost, you don't want to blindly simulate everything, right? You need to be able to basically decide what simulations you need to run, right? You need to be able to efficiently, right, so in parallel, execute what we call these coupled simulation ensembles, right? So you need to have actually a compute platform that basically supports that, right? You need to be able to analyze the simulation results, okay? As we will see, basically, the simulation ensemble, you may have many of them, and each one of them may be complex, right? So because each one of them is actually, we'll see that they are multivariate time series, right? So each simulation is a high-dimensional multivariate time series, right? You need to be able to actually analyze these results, right? So that you can find patterns, outliers, and critical decision parameters, right? And right? So to basically give to decision makers, right? And given real-world observations in a dynamic setting, right? So you need to revise and refine your models and ensembles as time evolves, right? So these basically what we call the DataStorm ensemble management services, right? So DataStorm, this is again a nation science funded project, and as I said, so there are multiple sort of different projects that are tackling different aspects of this, right? Including basically a recent grant that we have that tackles sort of co-optimization and co-decision making for epidemic modeling and rapid testing, right? But essentially the service involves, right, so generating possible futures, right, so from past observations, right? So, and this basically involves, as I mentioned, simulation ensemble generation, right? Simulation ensemble optimization, right? So first of all, I should start the other way. Simulation ensemble optimization, which means which simulations I run, right? Simulation ensemble generation, which is actually running those ensembles, right? So on available compute resources, right? And simulation ensemble analysis, which is basically, okay, now that I have these simulation ensembles, can I actually basically render these useful for a decision maker, right? So can I do that? Okay, right. So, and DataStorm essentially, as you can see, it has these multiple components, and each one of them basically essentially is a different research agenda in and of itself. Right? And one part of this, essentially, if I just focus on the simulation ensemble generation, right? So there is we developed what we call DataStorm Flow Engine, right? So which basically actually enables you to couple multiple independently implemented simulators, right? So you can have a hurricane simulator, you can have a flood simulator, a search simulator, a human mobility simulator, a disease simulator, right? And you can actually couple them, okay, right, in one single execution, right? And allocate simulation resources, right? So to these different tasks, right? Execute them in parallel, both basically the multiple models as well as multiple simulation instances per model, right? So per model, right? And you can actually also create timelines, which basically essentially sort of consistent views, right? So because you remember, for each model you are executing many scenarios, right? And these scenarios couple, right? So you actually need to maintain timelines, logically coherent timelines, right? So in time and in basically in this workflow, right? And basically execute them and create basically what we call continuous coupled simulation ensembles, right? These simulations, right? So at the end of the day, right? So they basically produce, right? So what we call what are multivariate time series, right? So for example, in this case, we have two simulations results, right? So each curve is a different US state, right? And this is basically two simulation ensembles, right? So based on the same disease model, okay, that they simply differ, right? So based on where basically the disease entered the US, right? So the outcomes could be very different, right? So based on where the disease enters the US, right? So and decision makers, right? So often not only interested in a single number, say number of deaths, right? So but if I'm going to be interested in the interventions, I also need to understand what these multivariate time series, what our individual shapes look like, right? So I cannot just basically say, give me just summarize everything to one number, right? So often you are actually interested in understanding what these time series look like, right? So this basically brings me to my last part of my presentation, which I'm going to take basically, I think I have 5 minutes, which I'm going to summarize in 5 minutes, which is basically, sort of multivariate time series understanding. Right, so we say complex, dynamic, human-centered environments. Complex to bring multivariateness, right? We discussed, and the dynamicity brings the time, right? So we need to basically provide, as I mentioned here, we need to provide basically ensemble analysis, which means we need to make sense of multivariate time series, right? Now it turns out that this is not only limited to this particular task, right? So it's not only limited to disasters, okay, right? So seizures, right? So and brain trauma, right? Again, another project that we have at Phoenix Children's Hospital, funded by Department of Defense, in this case, right? It's about basically addressing brain trauma in children, right? So that basically have seizures, right? So the question basically becomes, can we actually detect or even predict, okay, right? So the seizures, right? So early, right? So and in this case, the scale is completely different, right? So the data is high quality, often in this case, right? But then the time that you have for prediction, right? So it's under of seconds, right? Because you cannot predict things many times, these type of seizures an hour ahead, right? So, and basically detection is already too late, right? So because the kid is already in seizure, so it is not useful to detect, right? So because there are other physical evidences, right? So you need to detect maybe 30 seconds ahead, right? So maybe 1 minute ahead, right? So can you do that, right? So it turns out that basically this also involves multivariate time series, right? And it also involves basically this what we call spatial structure, right? So you have a spatial structure that basically ties the sensors that you have in the child's brain, right? Building energy, right? So it turns out to be very similar, right? So by 2030, right? So 82% of the US building stock, right, is expected to be on smart energy technologies, right? So this basically necessitates, right? So new services, right? So for optimization, energy optimization, right? But also for fault detection, right? So diagnosis, right? And also cause analysis, root cause analysis, right? So if you have a complex building and suddenly maybe you notice that something is not working, functioning as it should function, right? Maybe even an attack, right? So from an external network connection, because many of these actually infrastructures are going to be grid enabled, smart grid enabled, right? So this means that basically you need, okay, to be able to, right, deal, okay, with, again, multivariate time series, right? And again, it turns out that this multivariate time series is not only time series that you have, but you actually have a underlying spatial and topological network context, right? So because the observations that you make, right, so are linked to each other on a building. Okay, building is a spatial context. Rooms are next to each other, right? So they are connected basically with physical connections, right? So, but you also have basically heating and cooling units that relate to each other, right? So, and these might be separate, but the heating is kind of related to cooling, right? So they might be different devices, but they are related, right? And there is a basic actual physical communication network that ties them together, right? Okay, so there are actually multiple layers of network connectivity here, right? So from these, okay, so what comes to, right, so essentially, right, so can we discover key events in multivariate temporal data, right? So can we classify these key events? Can we predict future events? Okay, right, so good events or bad events, right? So fault, for example, right? Can we learn models underlying these events? Okay, right, so can we optimize for different outcomes? Okay, right, so can we optimize, can we cause events? Right, okay, and can we assess the robustness and resilience, right, so of a network system, right, so like a building, okay, or basically or a disaster response ability, right, so of a city, right, based on observations that we can make and simulations that we can run, right? So these basically become, okay, what we would call networked time series challenges, okay, because I don't want to call them purely multivariate, because they are not purely multivariate. Yes, there is purely multivariate, but you have a network that relates, okay, those variates together, right? So they are not purely multivariate. They are multivariate plus networked, right? Now, this basically sort of ties to sort of a set of other grants that we have. Of course, basically these grants are kind of related to each other because the data that produces from one set of grants kind of feed into the others. But essentially, basically what we call causal learning from time series. So this is actually the final part of my talk, right? And in this part, basically, what I would tell you guys, right, is this causal impact analysis, right? So basically involves basically moving a complex data to what we call context-sensitive impact models, right? Through summarized sample processing, incremental processing, prioritized processing, multi-scale, multi-resolution processing, using either tensor-based models, probabilistic models or neural network-based models, right? But I might be running out of time, so I'm not actually going to get into details of that. I have some interesting results, but I would rather not basically spend all the time talking. I would like to basically actually interacting. Let me ask the chairs how much time I have, and I will basically finish my talk accordingly. Ernesto, how are we doing with time? So would you like me to go 5 more minutes, or shall I basically stop now? Or,
I think you can go for 2 more minutes if you don't mind.
Okay, 2 more minutes. Okay, all right, that's great. Okay, 2 more minutes. Okay, so this what I will basically show you guys. At least let me show you guys one result. Okay, right? So whether we can efficiently identify, right, so search, analyze key temporal events in multivariate time series. Right? That's basically the question that basically I'm asking, right? So based on what we said, right? So what we have shown is that basically many times, right? So we can using the time series data and using basically the additional network or topology information, right? We can actually do what we call multi-scale analysis, right? So we can actually basically look for sort of what we call robust multivariate temporal patterns, right? So in these time series, right, which are essentially sort of parts of the series that are different from their neighborhoods, okay, right? So both in time and metadata, right? And they are maximal in terms of how well they are defined, right? This basically gives rise to what we call multi-scale analysis or scale space analysis, right? For extracting robust multivariate temporal features rather from time series, right? And interestingly, right, so this robust multivariate time series, right, so features, okay, right, so that you can extract through real-time pre-processing of the data, okay, that is continuously being fed, right, can actually be used for multiple applications, right, so multiple of the challenges that I basically actually listed you guys earlier, right, so I will show only one of them. Okay, right, so I have only 2 minutes and I will use one of them. So I will basically show you guys one of these, right? So one question is, right, so can we use RMT features, right, so to help select so relevant data streams? Think of a building, large building, okay, hundreds of basically sensors that are feeding basically data to you, okay, right? And you basically have one thing that you want to predict, say energy usage, okay, right? So that's your problem, right? So you have 2 options, right? So either you will basically use all of the 100 data series, right, and feed them maybe to a neural network and hope that the neural network is actually going to be able to do a good prediction, right? Or you will somehow try to basically reduce the number of variates that you have, right? And hopefully basically hope that in the reduced variate space, right, your the fewer variates that you have, right, so we'll basically actually be able to predict what you want to predict, right? So what we have done is, and this is basically one result, okay, right? So what we have shown, right, so is that in fact, right, so you by doing RMT-based variate selection, by reducing basically number of variates, right? So this is we call SELEGO, right? You can actually train much better predictors, right? So using, say, neural networks, it could be CNNs, it could be RNNs, it could be LSTM, right? Much better networks, right? So then you would basically do by using all of the available data, right? So this is actually good, right? So because you are reducing the data, right? So and you are actually able to predict better, right? Another thing that actually we have seen, right, so is that if you are able to intelligently select data, basically predict, you are selecting the most relevant predictors, right? You can actually use simpler models, right? So in this slide, for example, you have LSTM on one side, CNN on the other side, and CNN is more green, means better, right? So CNN is a much simpler model than LSTM. It's much less sensitive to noise, and it's much cheaper than LSTM. Okay, LSTM turns out to be, it is good, okay, right, so if you want to use all of the data, right, but it actually performs poorly, right? They actually say the other way. CNN actually performs even better, right? So if you can basically say, you know, this 95% of the variates are useless, let me just basically find the good variates and let me just focus on them, right? If you can do that, then CNN turns out to be actually a much better solution, right? And in fact, basically for this set of results, we basically considered, well, what about attention models, right? Because there are all these great attention models, right? So that basically supposedly help focus, right, on the interested parts. Okay, maybe attention actually is good, right? Attention actually helps, right? So to LSTM and RNN, attention actually gives you basically a couple of percentage points of improvement, right? But the real improvement really is coming, right, so from intelligent varied selection, right? Okay, and we have shown that basically this can be done. And we have also basically shown that, in fact, RMT, right, so it can basically be used for even developing more effective attention mechanisms, right? Again, I'm not going to go over them. I think I just ran out of time. There are some interesting results, but I want to finish with this, Ernesto, right? So this is basically the center that I'm leading. This is its vision statement. Again, it is basically created not by us, but by basically those companies that I listed at the very beginning, right? So today, the amount of data being generated is massive, right? And this necessitates engineering of new data architectures, okay, with lots of processing power and tools that can match the scale of the data, right? And that support split-second decision-making through data fusion, integration, analysis, and forecasting, right? To help non-data experts, which are basically the human consumers, right, to make decisions and generate value, right? And I would claim that basically smart data services, right, are really about this, right? So about basically developing a service infrastructure to support these this vision statement. And that's basically my team, my research team, my lab, as well as basically the center that I'm sort of leading, are essentially basically sort of are formed around these ideas. And with that, I will stop. I apologize. I think I ran a few minutes longer, but I hope you found basically the presentation informative. So I stop here. Ernesto, Felipe?
Felipe has to put me on stage, otherwise I can't. Okay, I'm here.
Yes, that's correct. Okay.
Well,
okay.
First of all, thank you very much. I will sort of interpret the audience.
Thanks a lot.
by clapping my hands. But then, well, I just wanted. I mean, it's been a very. I mean, thank you for taking us through this journey, right? In so many problems and so many issues you mentioned, so many solutions you sort of pointed at. I think that. I just want to ask you a question, which summarizes a little bit what I saw from questions from the audience as well. The question is about this. There are so many these days, so many, let's say, multi-view problems in which you get the data starting from different heterogeneous data sources. And of course, you have mentioned that during your presentation. And in many cases, we have a sort of let's say, we have an alternative approach in taking some early fusion approach in which we try to sort of bring the data all together to some ID-dimensional model, or in other cases, we want to have different models and then I use boosting. What is, in your experience, in your methodology, the right way to handle this problem? How can we decide what is best, or at least try to find so I understand that you showed us both worlds, right? But
I did.
I have to decide which world I should use. What should I do?
I did. So that's a very difficult question, right? So in the if you guys sort of remember, so in the sort of the cyclic sort of diagram that I showed, right? So I claimed, right, so that basically sort of data fusion, right, and data integration, right? So data unification, right? So is a sort of first step. Right, so that's what you do, right? And then after that, you feed this into basically your model learning, right? Which is kind of actually what most systems do, right? So you basically actually create your very unified vision, and then you might clean the data, right? Okay, you create one integrated representation, or maybe multiple integrated representations, right? And then you basically you then feed them into your decision making, right? Now, it turns out that is not always how it works or how it should work, right? So for example, in prior work, right, so we had actually shown that if you have conflicts, right, so if your data could have conflicts, right, so, and many times you don't want to actually resolve the conflicts too early, right, so because those conflicts, right, so may be valuable, right, and in fact, basically those conflicts, right, so might be what you need to keep, right? So you need to, when you explain your results, right? So you need to actually basically inform your decision makers, right, so about the existence of those conflicts, and maybe ask the decision maker to resolve those conflicts, right? So is in the part of a relevance feedback or conflict resolution process, right? So that actually requires, right, so a sort of a post, or not even post, but a representation that can actually keep conflicts, right? So you have actually keeping alternative interpretations together, right? You have a processing, right, so that operates on that alternative, that basically simultaneously operates on multiple interpretations, right, and basically shows the results to the user, right? So for cleaning, okay, so I have these possible results, right? So one is based on this interpretation, right? So one view of the world, one ontology maybe, right? So I have this other basically view of the other possible results. So this is based on another view and maybe another basic underlying ontology or metadata, right? Okay, other assumptions, right? And which one do you believe, right? And the user, one user might say, I believe this. Another user may say, I basically prefer this, right? And now you can actually basically do personalized basically sort of view selection essentially, or you can resolve the conflicts basically per expert or per decision maker, right? So that needs to be done late, right? And I didn't present that. Felipe, could we have my slides very quickly? Okay. Now, one of the things that basically we have also done, right? So is and I basically sort of skipped that, right? Is what we have done essentially, right? So there is some approach to machine learning called multi-head attention, right? So this is basically you basically have data, right? So you have your data has different modalities or different things, okay, in it, okay, and you basically have one head that deals with each one of them, right? And then you sort of basically integrate them as you mentioned, as the last step, right? So to decision making. Right, so that's basically sort of one sort of recent, okay, sort of neural network design, right? So it's called multi-head attention, right? One of the most recent basically results that we have, right? So is that actually this is not a good idea, okay, right? So because as we said before, right? So you have basically processes that are interdependent, okay? So these processes can be of different scale, okay, right? So it can be of different basically type, okay, right? But they basically actually have possible interdependencies, right? Which means that, okay, you actually need to, when you are developing your attention, right? So when you are sort of deciding what to emphasize, right? So for your decision making, right? So and you do this automatically, right? You actually need to deal with what we call this cross-head attention, right? So this is basically what we call multi-scale, multi-head attention, okay, with crosstalk, right? So because in this case, all these different processes, right, not only basically feed separately and connect at a single attention, but you actually sort of learn, when you learn what to attend, information from these different views of the data, right? So you actually learn you learn each head is a different view, and you learn what to attend, okay, through different views of the data, right? And what we have seen is that basically, if you do it like this, right? So if you basically use this cross attention, right? So across multiple scales, multiple views, right? You actually get much better accuracy at much cheaper cost, right? So to answer your question, maybe it was a long answer, right? But I basically gave, as you said, I gave two views, I mean, both views, right? So in the cycle that I gave the impression that basically things are good and you can just basically integrate before, fuse before, create a single view, and feed that view for decision making, right? Okay. Reality is more complex than that, okay, yeah. Right? So and you can actually get a lot of benefits, and we believe that that is critical, especially if you have multiple consumers, okay, right? So, and especially if your data is conflicting, so that you don't know actually. That goes to trust, right? You can trust something, I might trust somebody else, right? Okay, so if you have multiple consumers, right? So many times, right? So you cannot actually afford, right? So to do all your multi-view integration, cleaning, unification sufficient early. You need to let it. You need that need to go all the way through all of the processes, and what you show to the user needs to be explained in terms of the data sources, the original views, right? So that's important. Okay, so and so I will basically. I hope I answered the question.
No, you did. You did. Thank you very much, and you opened more doors than you. But anyway,
Okay.
It's always like that. So, well, thank you very much. This was a very inspiring keynote, and I was really very glad to be able to exchange ideas at the end. And also thank you for all the contribution that you delivered to the audience. I see many people are still with us, meaning that there was a lot of interest in
I'm glad to hear that. I'm glad to hear that.
So once again, thank you very much for being with us tonight.
Thanks, Ernesto, and I enjoyed this a lot, and I also enjoyed interacting with you, and I'm also honored that you were my you were my chair of the session. Thank you so much.
Okay, thank you everybody. Thank you. This ends the session, and well, thank you everybody in the audience for being with us tonight.